Very good afternoon, all of you. So now we are moving ahead with next session of day 3. So here, Dr. Andriy will be discussing about in this particular session about phase change mechanism and pressure-induced phase change. So now I would request Dr. Andriy to start with his talk. Yeah.
Okay. Good afternoon, everyone. So let us continue the first topic on phase change mechanisms. So this is a very important topic because, again, if we go back to our scheme from the first lecture, we have here the transition between amorphous and crystalline phases induced either by optical or electrical pulses. And so we want to understand these transition mechanisms, like from crystalline to amorphous and from amorphous to crystalline. Of course, we are also interested in the transition inside of crystalline phases, because it can also offer some new applications in this field. So up to now, there are several phase change mechanisms proposed in the literature. So they are listed here. This is possible amorphous crystalline and crystalline amorphous phase change mechanisms. One of the first model was proposed in 2004, and it's called umbrella flip model. The second model was proposed in 2006, and it's based on rings rearrangement model. We know that amorphous phase consists of rings like AB. Then there were also some model based on distortion triggered collapse, 2011, and then also in between was also like ring model rearrangements of AB units, also similar to this, but different mechanism, different approach. Also was improved 2013 and 14. Then we also look to the photo-induced amorphization, and then we also consider crystalline to crystalline transition, which we know that we have here different crystalline phases, and they are interested how this transition is occurring. So now let's consider this first model. Here, this model is based on the on XF's data, and this is just like a phenomenological model. So here they studied the bond lengths in the crystallite state and in laser amorphized state. They used real optical devices, I think CDRV, and then they looked to the bonds between germanium telluride and antimony telluride to the bond lengths. We know that in crystalline state also the such bonds also exist. And what they found that in laser amorphized state there is two types of bonds like germanium telluride and antimony telluride. Antimony telluride bonds they are a little bit longer compared to the germanium telluride bonds. They also studied the crystallized state, and here there are also two types of bonds, germanium telluride and antimony telluride. They are different a little bit, but not so much. And this, if you look to the environment of this germanium and antimony, we know that they're sitting in octahedral sites, like in a crystalline phase. But this bond length, it suggested that the germanium is sitting in the tetrahedral sites. And so in 2004, Kolobov and Tominaga, they proposed this so-called umbrella flip model. So what is happening here? We have crystalline phase, and on phase change between crystalline and amorphous state, the germanium, tetrahedral germanium, octahedral germanium, it shifts to the tetrahedral sites, and it brings to the distortion, high distortions in the system, and the system like collapses and transforms to the amorphous state. So it's based on the transition between octahedral and tetrahedral sites. So the next model, it's based on the rings statistic, or the fact that the amorphous state it's built of like units, small units, rings, different rings. We know already about this. And this is for your recap, this is a structure model from RMS and synchrotron data for GST225 and germanium telluride. And here in the amorphous state, there are different type of rings, mostly even number of rings in GST, like 4, 6, and 8. And in germanium telluride, they have a little bit more rings, type like 3, 5, 6, and 7 atoms. So they have 8 and even numbered rings. And here, if you compare the crystalline material of GST, GST has in crystalline state 4 rings, 4 numbered rings, 4-fold rings, and 6-fold rings. And here in the crystalline GT, they have only 4-fold numbered ring. And so, based on the local structure of amorphous state, one can propose a transition model from the amorphous to the crystalline state, and it happens during the several stages. If you start at the crystalline state of GST225, then we can go to the liquid state, and then here it amorphizes after high cooling. If you achieve high cooling rates, we can get amorphous phase, and this amorphous phase that consists of 6-fold, 8-fold, 4-fold, and 10-fold rings, and then these rings in the stage 3, these even numbered rings, they transform to the crystalline state without bond breaking. In the case of germanium telluride, here this is the situation little bit more complex, because there are odd rings like 3, 5, and 7, and in the stage on the way from amorphous to crystalline, somehow the bonds like germanium homolar bonds, they should rearrange to the germanium telluride bonds and then form this crystal structure. So next model, it's based on the distortion triggered collapse model. Here, this model is just was studied solely in computer. So here the authors, again here Kolobov, Tominaga, they proposed two structures, considers two structures. One is the structure 1, and in this structure the germanium atoms were displaced along the one direction to minimize atomic misalignment, and in the structure 2 they allow germanium and tellurium atom to displace to maximize atomic misalignment. Then they relaxed the both structures, and they found that if we have a minimum distortion of germanium atom, then the structure can go back, transform back to the initial structure, so it relaxes back to the equilibrium structure. But if you have a high distortion in the system, then system cannot relax back to the initial state, and so it transforms to the disordered structure. So large distortions in PCM can trigger this destruction of the subsystem of weak bonds, and this results in collapse of long range order and transformation to the amorphous phase. And by this also this mechanism can be also considered as non-thermal phase change, and also it suggests that it's possible, and if you somehow can make it possible by experiments, then you can transform from the ordered to the disordered structure simply by distorting the germanium and tellurium atoms, both of them. So now the next model, it's based on the AB units rearrangements. Again, as I said, we know already that the amorphous phase that consists of A, B, and B rings. A, this is germanium antimony, and B, this is tellurium. And they make so-called AB square in the material. Such squares also also exist in the crystalline state, and this mechanism based on the rearrangement and of such AB ring to the ordered AB rearrangement of such squares to form ordered lattice. So in this model, in the crystallization process, we start from the amorphous state consisting of these AB squares, and they considered as precursor in this system, so like a nucleus. However, it requires at least 10 to 50 atoms to form such a nucleus, and then if they have been formed, then the system starts to crystallize. This is the nucleation process is a statistic process. It requires some times. So there is nucleation, percolation in the early stage, and then if they form some stable nucleus, after some times you see it requires, like, the system can form nucleus and then go back. But if some stable nucleus have been formed, then the system can start to crystallize, and on the picosecond scales here. So just to get an impression how it's going on, so that yeah, you see that the nucleus, so systems try to form nucleus, and then as soon as it's formed, it starts to grow. And now here we have here some nucleus, some here, and as soon as it's formed, the materials is crystallizing. But as you can see here, this is a stochastic process, and this stochastic nucleation, it prevents the optimization of memory writing time for poor GST and germanium tellurium alloy. This knowledge is very important, because if you want to optimize such writing time, we need somehow to, maybe if you introduce some doping, to stabilize this nucleus and to induce the nucleation in particular sites. We will see it in the last or in the next lectures, how to prevent this stochastic nucleation and how to optimize the writing times. So now this is also mechanism model called photo-induced amorphization. It's similar to the model which based on the high distortion model, in the sense that it's like considered like a non-thermal phase transition. So here, this if we have a cubic GST, and if we are excited by the laser, by femtosecond laser, then we can, by photoexcitation, to transform this crystalline state to the somehow transient structure which exists at 100 femtoseconds, and then at this state, the so-called metavalent bonding at that time in this publication, they claimed it was resonant bonding, but it's metavalent bonding. The system lost this, and then afterwards it's due to the energy transfer to the electrons and to the lattice system. It heat ups locally and then melts. So there is by process of lattice heating, the system transforms to the liquid and then to the amorphous state. So this occurs on a time scale like around 5 picoseconds. So this is also like non-thermal process. Also, in this publication, it was also shown that that by using femtosecond electron diffraction and structure factor calculation and some simulation, it was revealed that also possible to suppress local spiral distortions. You know that this system cubic GST, it's highly distorted, also poses like so-called pulse distortion, and then it's possible to suppress it in crystalline GST within of this 0.3 picosecond. So just to again to maybe to change the one from one bonding state to another bonding state. So now let me consider some crystalline phase changes. Such crystalline to crystalline phase changes can be nicely studied by in situ or ex situ methods. In this case, we performed in situ electron microscopy, and we observe. We were interested in this crystalline to crystalline transition. So particularly in the CGST phase. So what's happened if we find such a large grain in our thin film, and then if we heat up, what happened if we can observe another phases, like as an ex situ TM. So if we heat up our cubic GST from 150 degrees C to 160, we observed the transformation from cubic to vacancy ordered phase. So this is the high resolution image. It shows the random distribution of vacancies in this cubic phase. And then at the temperature like 220 degrees C or 160, we can start to see such lines in this system. And this is a signature of this formation of vacancies. It can be also confirmed by selected area electron diffraction. Here, this is the cubic lattice. It's highly ordered here. It is like single crystal. We see main reflections coming from the structure, and in the vacancy ordered structure, we see additional reflections which lie on the 111 planes. So these vacancy layers, they are formed on 111 planes in the cubic lattice. This can be also nicely seen in the HADF image. As I said, it's a more convenient method to observe real crystal structure. And this is again this large grain. It transformed to this vacancy ordered phase, and these dark lines in this image, they represent vacancies which are formed on 111 plane, and then this is another 111 planes in the cubic lattice. So the transformation from vacancy ordered phase to the for example to the trigonal phase can be also studied by in situ X-ray diffraction method. In situ or X-ray diffraction method, I think it's well-known method, also available here. It needs filter, but here in this case we also use the heating stage to heat up our system containing vacancy layers. This is epitaxial thin film, and if we start to heat up our epitaxial thin film, we can go through different phase transition, mainly from one. So we can see here we start the vacancy ordered phase, and then at this temperature 200 degrees C, we observe the formation of additional peak, which is then growing on the temperature 210 to 240 degrees C. And this peak, this belongs to the TGST phase. This is stable trigonal phase. So here we can nicely observe the transformation from vacancy ordered phase to the TGST to the trigonal phase. And here, this is atomic resolution image that shows you this highly ordered TGST phase, first vacancy ordered phase here, and then this is the TGST phase, where we know that if there is transformation, the structure, it has hexagonal stacking. And here we also look to the mechanism of this transformation. We found some interesting areas here. So one part of our grain, it still shows here. This is hexagonal stacked, so this is trigonal phase. Here's a cubic vacancy ordered phase. Here's also vacancy ordered phase. And in between we see some contrast. So we see how the lattice shifts one to each other, and how the atoms, like here, they have doubling of these atomic columns, and it suggests that the transformation occurred by small motions, atomic motions in this direction. So the system like shifts one against each other. This was also nicely confirmed before our publication on the system antimony-telluride, how this process occurs. So in antimony-telluride, we have also can have two also vacancy ordered phase. And if the and then if you use DFT calculations, and if you try to shear these blocks, so the antimony telluride consists, as you know, from the building blocks, quantipoles, here layers, vacancy layer in between, and then if you like make the shearing here of the blocks, then they can transform from one phase to another phase. And here we have two steps. One step is the shearing of the building units, one against each other. Here you can see this is if I make the line. So here can be seen maybe more better here. If you take this atomic row, then if you make the shearing, it's transformed here. And then we need to contract the system to form van der Waals-like gaps. They also showed that this transition, it's possible to go back from the stable trigonal phase to the vacancy ordered phase, but it's more complicated process, and actually we have not observed it until now in our work. Also, it's possible to transform between the phases, like between TGST to the CGST phase using laser. And this is so-called, we called it like interface-assisted amorphization. And here, in this case, if you have this TGST, the stable trigonal phase, epitaxial thin film, you can see here our system. And if we irradiate this system by UV laser with pulse duration 20 nanoseconds, this is the wavelength 248 excimer laser in this case, then we can transform our TGST to the cubic GST. But in this case, this transition occurs not through solid-solid transformation. So it's not crystalline to crystalline transformation. It's more like that during this pulse duration, 20 nanoseconds, we melt our system, and during the cooling, the system recrystallizing, and then the system goes back to the CGST phase. And it shows, so here this image shows this transformation. So this is the same thin film, and the part of the thin film transformed to the from TGST to CGST, but by melt quenching process. Interestingly, that although there is a like template in the case of TGST, and we would assume that the like vacancy layered phase could be formed here, or TGST phase. No, it's not formed. So because during this process somehow the system forgets about the previous structure, and then there is a transformation to the metastable CGST phase. But it can be also used if you think about the multi-level data storage, if you can adjust the pulse duration or also the energy of our laser, we can adjust the volume of the transformed phase. So from high amount to the low amount. Here we can show this if we just like if here in this case it was the fluency of laser 31 millijoule per square centimeter, and then if we increase it, we can go completely to the cubic phase to CGST. So here they increase the fluency of the laser, but again this is the melt quench process. We transform first the phase to the melt, and then it recrystallizes into the cubic phase. If you want to go to the TGST phase, we can make the annealing or heating of this CGST phase. Then we go to the different phase transition like vacancy ordered phase and then TGST. And if you want to go back to the CGST, they use the laser radiation. So it shows some possibility of just like phase tuning by using heating and the laser irradiation. And if you can realize this in the device, we can maybe use it for data storage, for optical data storage. So now I would like to conclude this part of my talk. So we considered the umbrella flip model, which is based on the transformation of tetrahedral germanium to the octahedral side, tetrahedral germanium in crystalline to tetrahedral side, and then it brings the system to amorphous state. Then the rings rearrangement model, here the ABAB rings included, and it's based on the reorientation of these ABAB rings. This distortion collapse model, based on if we can induce high distortions to the system, we can transform crystalline state to the amorphous state. This is non-thermal process. And if you have some idea how to realize it, it would be really nice to see it. Again, ABAB units rearrangement. Here, here it was done more work, theoretical work, and it was shown that if you want to crystallize your system, first you need to form such ABAB squares, and this acts as nucleus, and then they squares and cubes, and then they transform to the stable nucleus, and then the system starts to crystallize. But the problem is here, this the nucleation. This is non-homogeneous process, stochastic process, and this hinders the optimization of memory time for pure alloy. So we need here some ideas how to stabilize this nucleus. In the photo-induced amorphization, here ultra-fast photoexcitation, it shows the formation of additional phase, like first the cubic phase, it transforms, it lost his bonding, metavalent bonding, and transforms to the convalent state, and then it melt by energy transfer to the system, lattice system. The phase is heated up and transforms to the liquid, and then on cooling to the amorphous state. And then we also consider some crystalline to crystalline phase transition between cubic and vacancy ordered, and vacancy ordered to trigonal phase. It's here we saw that it occurs by atomic motion on very short distances. So do you have some question on this part of lecture? If not, maybe you can ask after. Oh, please. Yeah.
So, Professor, in slide 10, you were discussing that in vacancy ordered structure, the temperature holder is 160 to 220 degrees.
Yes.
So, is this the rule of thumb if you want to create a vacancy ordered in GSTs? Like we need to keep it 160 to 220 degrees. So that is when we get the vacancy ordered GST.
Yeah, it's a little bit composition sensitive. For GST 225, it's we can take it like so it's so because we can create a stoichiometric GST 225, we use in situ heating, but we also compared with ex situ heating, and this vacancy order it really occurs in this temperature range. If you remember this, this RT measurement, it starts like from here, like little bit maybe larger here temperature, but it's in the range between 170 and 200. Can be a little bit extended, but the problem here, we will discuss that here at some temperatures you have a mixture of vacancy ordered and trigonal phase.
Okay.
Because after 220, we observe the formation of both phases. Mixture. But for vacancy ordered, there is a window. You have to identify for your system, because it's compositional dependent and also it's thickness dependent.
Okay.
So, and also it's also heating rate dependent, how fast you heat your system.
All right. Okay. Thank you.
Because I think some data shows if you heat it very fast, you can overcome this window with very short. So,
Short.
Yeah.
Okay. Thank you. And in slide 12, we were discussing about the impact of bond length in shearing and contracting. So can you just stress on it in terms of reliability?
Okay. This is just a mechanism how this transformation occurs.
Okay. So it doesn't affect if we reduce the bond length by shearing and contracting. Where this like the bond length will decrease or increase if we do shearing and the contracting.
But here this model it considers the really movement of these building units.
Okay.
So there is no bonding break. So
that doesn't reduce the bond length.
No, it's not reduced. It's like
Okay.
they are like shift here, maybe here. If you see here that the atoms shift here on a very short distance.
Okay.
So there is they assume there is no bond break and maybe a little bit contraction, but not large.
Okay.
If you want go back, here we need to break some bonds. It's more complex mechanism.
Okay.
But here it's just they assume the transformation of these building units like sharing of whole atoms.
Okay. All right. Thank you.
So more questions? If not, then I will continue with pressure-induced transformation. This is also interesting topic from point of view of basic research, but also it's very interesting for applications because it allows us to study the behavior of different phases under extreme condition, like if you want to use these materials in space or whatever. So again, this is just for recap. You know already that there are different type of phases: amorphous, distorted pseudocubic phase 1, distorted vacancy ordered phase 2, and the stable van der Waals-like bonded phase 3. And here we will look on the phase transformation of these phases under pressure. So if you set these phases under the pressure, what happens if you just press this cubic phase? What happened if there are maybe some new phases formed, or here maybe can induce some amorphization or new phases like this? So how does it? How can we study this phase transformation? So for this we need a special setup, and it's based on the diamond Abel cell DAC setup. Here this is the image. It shows two diamonds, and here this is the how GST powder, and by like moving and pressing these two diamonds, we can reach the pressures more than 30 gigapascal. And because the amount of our powder is not so large, we study this transformation using in situ X-ray diffraction mainly by synchrotron. And of course, it's possible to connect some electrical resistivity measurement to this powder. But here the problem that the contact of the electrodes to the powder. But this is how can be this also resistance of the phase change materials can be studied during this transformation. So now let's look to the pressure-induced amorphous to amorphous phase change. So if we press, let's say the amorphous phase, then what happened is, and to set the phase up to 8 gigapascal. So what we can see a drastic change of the resistivity here. This is several order of magnitude, so it's decreasing. But this is the reversible process. During this process, there is a minor change in coordination number, and also minor changes in the nearest neighbor distance bond length, and average bond length also stays almost the same. But what happens here, the simulations, they showed that if we compress the material, then the number of voids existing in this phase, it's starting to rapidly decreasing. So the fraction of this you see here, if it goes from this state to this, the number decreases. It can be also quantified. So in this case, what we have the transition from less dense to more dense phase under compression, and this more dense phase, it has different properties as the less dense phase. Then if we increase the pressure from 8 to the 28 Pascal, then this phase transform to this dense phase. We will call it amorphous phase 1. It will be transformed to the amorphous phase 2. Here in this case, the bond angles here in this state starts to decrease at 8 gigapascal. Also, there is increase coordination number under compression, and so here we transform our this dense phase amorphous phase to the amorphous phase 2, and then which is a more ordered phase compared to the both phases. And then on further densification, we can transform. We go to the transition to the crystalline phase. It's around 30 gigapascal, and this phase is not. It's also cubic phase, but it's not FCC structure. It's BCC structure. This is also highly disordered phase. And all elements like tellurium, germanium, antimony, they are located on each side, and there is no vacancies in this phase. So this transition reversible here from one phase to another phase. Now let us look to the pressure-induced amorphization of cubic GST and memory effect. So many materials, they possess this peer behavior due to presence of vacancies, voids, or weak van der Waals interactions like zeolites, porous silicon, fullerenes, molecular crystals. And let us look to our system, to the CGST on compression and decompression. So if we start and they consider two. This is not CGST, this is crystalline GST 225. So we consider two phases, cubic phase FCC GST and TGST. So on compression, if we compress this phase, we induce amorphization at this pressures between 15 and 25 gigapascal. And then on further compression, we get a BCC GST phase, as in the previous case, at pressures more than 30 gigapascal. If we compress the TGST, then we go to the orthorhombic GST, and then again to BCC GST. On the compression, if you go back, then the BCC GST, it transforms to the amorphous GST, which is similar to melt quench phase. So it does not transform back to the FCC GST. It's rather transforms to the amorphous phase, and it shows this amorphization using high pressure. However, in the case of TGST, there is somehow a memory effect, and if we decompress this BCC GST, then we go back to the phase like TGST. So this is the reversible process, and this is so-called memory effect in this phase. So somehow this phase it knows about the previous phases, crystalline phases, and then it reverts back to the TGST. Also, there is also change in the properties of the phases. Like if you compress the FCC GST, it's the resistivity it's changing on loading here, and then on the compression it's going up to higher value, showing the formation of the amorphous phase. So now let us look to the compression and decompression of the germanium telluride. Here the process of compression of germanium telluride, it leads to the formation of a cubic structure, Roxel structure at 3 gigapascal. It's transformed from the T structure, orthorhombic or trigonal structure, to the Roxel structure at 3.3 gigapascal. So we can see that there is no amorphization here, and also there is no reversibility to the initial structure in the case of germanium telluride. Also, there is a change in the resistance in this case. So it reduces from low pressure to the high pressure. So ab initio molecular dynamic simulations, however, they suggest some reversible phase transition from rhombohedral to Roxel type structure, confirming this result. Then to orthorhombic structure, again, experimentally it's also observed, but then they observed a new monoclinic structure having such semiconductor and metal interconversion under the pressure. So they observed this new formation of new phase, which was not observed experimentally. So now let us look to the germanium-rich alloys. What happened here for GST for antimony 2 tellurium 7 or germanium 8 antimony 2 tellurium 11. This is cubic. This is rhombohedral, and on compression we observed here amorphization at 22.6 gigapascal, and this phase transition sequence, it's similar to the phase transitions in 2 to 5 and 1 to 4 phase. On the compressions, this phase amorphous transform to the amorphous phase, so it remains. In the case of another germanium-rich phase, also on compression there is a transition first to the cubic phase and then to the amorphous phase. On the compression there is a back transition to the from amorphous to cubic phase, but not to the rhombohedral phase. But in both cases we observed so-called pressure-induced amorphization in these both alloys. And now let us consider shortly the mechanism of this pressure-induced amorphization. So from several examples, we have already seen that pressure-induced amorphization, it happens in the system with high number of vacancies. Germanium telluride does not have these vacancies in such amount, so this pair, it does not occur here. But in these all alloys, we have seen the amorphization. And this amorphization processes, it's was proposed a model called on anti-side hopping mechanism. If we consider our structure, like cubic structure here, consists of germanium, tellurium, germanium, germanium, tellurium. This is the cubic FCC. And then we have here vacancy. What happened here during the compression, we know already that the system can get a little bit denser. And here, what happens that tellurium, it shifts to the vacancy, like here. And then we have a new structure here having tellurium, germanium, germanium, tellurium. So it forms like AAA tellurium ring. The A, this is germanium and antimony. And then we have here a new bonds, formation of new bonds here, like homopolar bonds, germanium, germanium, then germanium, antimony, and others. So here we do not have it because tellurium was sitting here. And so there are two importance of vacancies in this system. That first, the vacancies increase the compressibility of the cubic GST and allows reaching a high density of the phase. And second, that if such rings formed, they, due to this homopolar bonds, they destabilize the system. And if the amount of number of such rings increasing and sufficiently high, then the system like destabilized and transformed to the amorphous state. Also, some phase changes in the other system in germanium-free alloys like antimony telluride, IST, and antimony telluride. In the trigonal SB2T on compression, this phase is transformed to the orthorhombic phase, then to the transformed to the BCT, and then stays this phase until 28 gigapascal, or here this transformed to the BCC. Sorry, it's mistake. It's BCC. Should be BCC. And then the BCC transformed back to the BCT. So again, here there is a crystalline transition, but there is no memory effect like in this case of the trigonal phase. AST, it's transformed from A7 structure to the BCT, and then BCT to the back to the A7 structure. So here we see the reversible process, crystalline process. Then in a square like rings, and then we have here formation of some homopolar bonds. And if you have enough of such high amount of such units, then the system just transforms to the amorphous state. So it's like, yeah, based on the atomic movement. So, yeah. But this is one idea how it can happen.
Any questions? Anybody else? So, in this your pressure-induced mechanism which you have shown, so just I wanted to know, is it possible in this particular setup which you have done? So we can check some kind of a switching mechanism with respect to pressure, how the electrical parameter. Is it possible in situ? Some kind of arrangement can be done in such kind of setup.
I think the one problem here is the space. We have a limited space.
Oh,
But yeah, maybe it would be possible if this question is really of high interest. I think this is, I think, technical issue as everything in our life.
okay, okay. Because the way I have seen you have done some 4-probe measurement.
Yeah,
On
this was not done by me. This is literature data.
Literature, I mean, yeah, it is there.
Yeah.
So, if possible, if we can do in that direction, so also, what is the effect in that?
For optical measurements, the setups are really large, so it's different. But nowadays, also ellipsometry setups, they are also shrinking for some applications. You can have small setups, small. Maybe someday somebody will study this. Of course, it's very interesting to look optical properties under compression, what happens. So there are some changes, as we have seen, resistance change, but what happens with optical, with the electric constants? It's really interesting. The band gap, it would be really very interesting.
And one thing you mentioned while discussing about this pressure-induced, the potential application in space or somewhere. So I think you have done some kind of this phase change mechanism, or have you seen any work on this direction on radiation effect on this phase change mechanism? Is there any, because just I'm curious to know about this.
Yeah, there are very many tests, like you can produce your phase change device and then you can send it to NASA, and then they can send it to the space and then make tests, and it works. So the radiation, it has not large effects, but there are some projects in the USA. I heard these talks. It was really impressive.
Okay.
They could test it after 6 months in the space. So it's nice. There is no really influence on the characteristics, so it's still working. But it's limited time, 6 months. So maybe if you let it for more years, maybe it's will be a little bit different. But with appropriate shielding, I think it will work.
Because in adverse condition, to identify this phase change mechanism, I think it's very important to understand.
Yes,
it could be the open problem for to see. Yeah. Thank you. So if no questions, then we can stop here. So I think this is the last session of today's our GAN course. Okay. So now we can go ahead for high tea, and then we'll wind up today's session. Okay. We'll meet tomorrow at 10. Okay. Thank you. Thank you so much.
Thank you.